In this video, we'll talk about permutations, what they are, and a couple of ways to calculate them. There's two approaches. One is more of a theoretical one, where you're thinking about how many ways there are to do something, and a second approach would be more of a formalized approach. So let's talk about what a permutation is. So a permutation is a way of counting possible outcomes where order matters. And that's very important. We'll talk later about combinations where order does not matter so much. And what I mean by order mattering would be if you think about a combination lock, one where you have dials with numbers and there's a particular code that will open the lock. It's going to matter what number comes first. So if I know a 3 comes first, that's going to be different than, okay, say if I have a 3 somewhere in the code. Order would matter in this case. So before we get too heavy into how to do them, there's one definition we need to talk about really quick, and this is more for the formula side of things, which can be kind of important when you're talking about really massive permutation amounts, when there's a lot of potential to, I guess, have a really big number. So factorials. In mathematics, it has an exclamation point, and there's kind of two working definitions that one can use. The first being, say if you have, say, 5 factorial, this is going to be equal to 5 times 4 times 3 times 2 times 1. So basically I'm just going to take every integer number, or I guess every natural number, from whatever number we're looking at, and we're going to multiply it by each one that comes before it. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. Now this is the more simple definition, I guess. It's easier to think about it this way, and as long as this one makes sense to you, that's fine. There are a couple finer points that it does miss. The more textbooky definition starts with defining what 0 factorial is, and they're saying that 0 factorial is 1. That's just how it's defined. And then you would consider n factorial to be n times whatever n minus 1 factorial would be. So in the case of 5 factorial, this would be the same as 5 times 4 factorial, since 4 factorial would just be this 4 times 3 times 2 times 1 piece. It's a more technical definition, but they both mean the same thing. So as long as one of those makes sense to you, you should be fine. So when we're looking at permutations, and remember, that's a way of counting possible outcomes where order does matter. And the typical example is a combination lock. So if we're thinking about a combination, there's a couple of possibilities that pop up. Do I have numbers that repeat, or do I not have numbers that repeat? And that's going to dictate what you do, and this is where we're going to look at the formulas approach. And when we go through the examples, I'll walk through both possible approaches here. So if we know there can be repeats, this means that, once I have a 3 on my first dial, well, then I know there could potentially be a 3 on each one, but it might not be. What we would do in the formula, and we'll define what n and k are here in a second. So I take n to the power of k, where n would be my possible choices for each slot, I guess. So in this case, in the case of the combination lock, we're looking at 10 possible characters, 0 through 9 for each one. So in this case, we'd have 10. And k would be the length of the code in the case of the combination lock, or the number of items chosen from n. So if it was a 4 length code, if it had 4 symbols, 4 digits, there'd be a lot more possibilities versus the 3. Okay? And if there are no repeats, this is where the factorials come in. You're going to take your n factorial, and the same n as it is over there, that'd be the number of possible choices for each dial, divided by n minus k factorial. And we'll talk about it. It might not make a lot of sense right now, but once we go through an example, it'll make a little more sense. So let's take this combination lock idea. Let's say we have 3 dials, 10 characters on each. How many possible combinations can I have? Now, explicitly in here, they never state that any number can't be repeated. So there's a lot of ways you could think about it. Let's take the less formalized approach first. Basically, what's happening here is I have 3 possible dials. I have a code that is 3 in length, and I have 10 choices for each possible slot, so to speak. I could have 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. We're looking at single-digit cases here, potentially. Or it could be letters. Whatever it is, I have 10 choices for each. So let's say I have an option that I pick for the first one. Well, off of each of those, there's 10 I could pick for the second. And off of each of those 10 that I could pick for the second, there's 10 more I could pick for the third. So we can think about this as a multiplication problem. It's 10 times 10 times 10, or 10 cubed. Now, if we think about this in terms of the formula approach, the number of dials is 3, which would tell me that I'm picking 3 things. So in this case, K is 3. And there's 10 characters for each one. So on each of those, I can make 10 possible choices. So in this case, N is 10. And if we follow our formula here, we ask ourselves, okay, can I have repeats? The answer is yes. And then we would ultimately follow the formula n to the power of k, which we see right here. Now, whichever way you think about this is fine. Just ask yourself, can I have repeats? Can I not have repeats? In these ones, it can be pretty simple to think about it either way, depending on what you're thinking about. However, if we're talking about a combination lock with 10 dials, and each character, let's say we're using all the letters of the alphabet, there could be 26 on each one. It might be more beneficial to just go straight to this approach as opposed to writing out 26 times 26 times 26 10 times. So let's take the same combination lock, and let's say no number is repeated. So again, 2 ways we can think about it. We can take the more theoretical approach here, and we can think, okay, well, if I think about my first choice, I still have 10 options available to me. So that number hasn't changed. There's 10 options for the first one. However, once I've picked that number can no longer be used. So let's say it's a 6. That means that, okay, on the second spot, I have 1 less option to choose from. So in this case, 9 more choices. And then a very similar line of thinking. The third one cannot be the same as either of the first 2, so that leaves me only 8 choices. Now again, I would just multiply these numbers, and that's going to leave me with 720 possible combinations in total. Now if we take the formula approach, in this case our n and our k are the same as they were before. So n is 10, k is 3. So if we think about what that means, we can take, following our formula where we have n factorial over n minus k factorial, let's just plug in the numbers and see what happens. We're going to have 10 factorial over 10 minus 3 in parentheses, then we're going to take the factorial of that, which, if we follow our reduction, we'll have 10 factorial over 7 factorial. Now, there's a lot of ways you can think about this. So if we expand out 10 factorial a little bit, we'll have 10 times 9 times 8 times 7, and I'm just going to go ahead and write this as 7 factorial because technically it would be times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then we're going to divide this by 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1. So even if I was to expand it all out, we would have a massive cancellation. So I'd have, let's go ahead and write it out just to demonstrate. If we go through with this, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then we divide that by 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, we can cancel out all the 2s, the 3s, the 4s, the 5s, the 6s, the 7s, or the other option would be, as soon as I get it to this factorial over factorial business, I can just cancel those out, because they are the same. And that leaves me with 10 times 9 times 8, which we had right up here in the very beginning. Now again, these two examples that I've chosen to start with, it's probably easier to just go through with the thinking. However, if we're looking at more complicated examples, which we'll look at in a second, it's more beneficial sometimes to take the formula approach. So let's look at a particular example where it's a little more nasty. So let's say we're looking at, okay, how many ways can I draw 5 cards from a deck? Now this one is a little bit different from our typical thing. We're not talking about a hand of cards. We're talking, okay, how many ways can I draw 5 cards off the top? So in this case, order does matter. If I draw an ace of spades first versus an ace of spades fifth, that's a totally different situation. So if I think about it, I have 5 possible cards that I'm going to draw. So we'll go with the theoretical side, and then we will go through with the formula side of things. So in my first card, I have 52 options. The next one, 51. The one after that, I have 50 times 49, and then 48. You can multiply all these numbers, and that'll tell you how many possible ways you can draw from the top. Now, the other approach is our number of cards that we can pick from is 52. We are drawing 5 cards, so in this case, our K is 5. That's how many I'm picking from. Okay? Now, again, follow the formulas approached. I can't have repeats. I can't have 2 aces of spades here. So we're following the no repeat formula where we have n factorial over n minus k factorial. So in this case, we're going to take 52 factorial divided by 52 minus 5 would be 47 factorial. Now if we expand this out just a little bit, we'll have 52 times 51 times 50 times 49 times 48 times 47 factorial. I'm going to stop there because that's what we have in our denominator. Those will cancel, leaving me 52 times 51 times 50 times 49 times 48, which is the same thing we had here. I don't know what that number is off the top of my head, but I can run in my calculator easily enough and crunch it. So that's a case where it might be about equal on which way you want to think about it. Now with a lot of these, you can argue either way, and that's why I go through both methods, depending on which one you like. Now we could be asking the question, how is this useful? And that is a good question. This is useful in that if we're trying to calculate probabilities, it can be important to figure out, okay, how many possible outcomes are there? So take this deck of cards, for example. Let's say we're looking at poker hands, and we want to know what's the probability that I can draw 4 aces out of the deck if I draw 5 cards. These are the kind of things we need to be able to do before we can calculate the probability. So it's more of a stepping stone into probability.